Hey, welcome back, everybody. We are moving on with Chapter 5. Chapter 5 is going to include some of the more challenging graphs. In fact, in my opinion, the most crazy graph is going to be the one that I'm going to describe right now for you, called a rational function. So just take your time with this. Rewatch the video if you need to, but this is just an introduction. But we will be graphing these things by the end of Chapter 5. All right, a rational function is basically a polynomial divided by a polynomial. And if you recall with a rational equation, there are times when we have to be careful that we're not dividing by zero. And so for example, let's back it up here. We'll get to the other in a second. Holes. Holes occur in graphs when we can divide out a factor. So for example, if we have this function here, and you can see x cannot be negative 4, even though I can actually reduce it out. And when I do reduce it out, we have that y is equal to x plus 3. Now, I want to point out when x equals negative 4 here, we get that y equals negative 1. So there's going to be a hole at the point negative 4, negative 1. And I want to show you what that graph is going to look like. So 1, 2, 3. Up 1 and over 1. So we are going to be here, and I'm going to put the hole in that is at negative 4, negative 1. I have to draw that bigger. So we are going to have a hole right here. And otherwise, we are going to be the graph that goes right through like that. So it's just the regular line, it's supposed to be straight, with a slope of 1, so up 1 over 1, and a y-intercept of 3. And so it's the regular line, but you have to put the hole in there. We have to acknowledge that x still cannot be negative 4. All right. Holes usually don't occur with these, but we got to keep an eye out for them. Next up is the vertical asymptote. And this might be notation that you've never seen before. If y is approaching negative infinity or positive infinity, that's up and down, y is, so if the graph is going up to infinity or down to negative infinity, as x is approaching a specific x value from the left or the right, then x equals c is a vertical asymptote. So for example, we may end up with something like this. And this is a graph that you probably recognize. And actually the y-axis here is a vertical asymptote. That's x equals 0. So this is a vertical asymptote at x equals 0. Meaning the graph is going to get closer and closer and closer, either from this direction or from this direction, and it's going to go off to infinity or negative infinity, depending on which direction we're going. But that's what a vertical asymptote is. Horizontal asymptote is a horizontal asymptote. And the line y equals b. So notice for the vertical asymptote, it's the equation x equals a number. For the horizontal, of course, it's going to be y equals a number. And y equals b is a horizontal asymptote of the graph of f of x if f of x, as it's approaching b in the y direction, as x is going to positive or negative infinity. So now, even this graph, we can see there's a horizontal at the x-axis, meaning it's going to get closer and closer. As x goes to infinity, the graph is going to get closer and closer and closer to y equals 0. Same here, to negative infinity. Now, you might have heard it said that you cannot cross an asymptote, and that's not true. There are occasions when that does happen and it crosses it once or even lots of times. The point is, as x goes to infinity or negative infinity, the graph is getting closer and closer and closer. So I want to point out that there's a horizontal asymptote at y equals 0. That's the x-axis for this particular graph. And just FYI, this graph is f of x equals 1 over x. All right, so those are horizontal asymptotes. We'll talk more about those in a moment. And what we're going to do with these examples here are talk about, and in fact, I want to put the cart ahead of the horse here. So I'm going to go through this and then I'll apply it here. So if we're given a polynomial in the numerator and a polynomial in the denominator, and this is a generic polynomial of degree n over degree m, and if the degree in the numerator is less than the degree in the denominator, meaning n is less than m, so larger degree in the bottom, then the horizontal asymptote is the x-axis, y equals 0, just like we had up here. If they're the same degree, meaning m and n are the same exponent, then there's a horizontal asymptote at the leading coefficient. So a sub n over b sub n, because m and n are going to be the same when they're the same degree, when they're equal. So it's just those lead coefficients, and we'll see an example of that in a moment. Now, if the degree in the numerator is bigger than that in the denominator, meaning larger exponent here than down here, then there's what we call a slant or an oblique asymptote. You'll hear me probably call it the slant asymptote. That's the way I was taught. The number degree must be exactly 1 degree greater than that on the denominator. That's not always true, but for this class, we're going to assume that that has to be true. What we have to do then is divide the expression to find the slant asymptote. And we'll do an example of that in just a moment. However, I do want to apply that to here, to these 3 examples here. So you see the degree is the same here. That means that there is a horizontal asymptote at, again, the lead coefficients, 3 over 1. So y equals 3 over 1, or y equals 3. There's a horizontal asymptote. I'm sorry, that's a 2. This one's smaller, so there's a horizontal asymptote at y equals 0. 2 is smaller than 3, so it's this first case here. And our horizontal asymptote is at y equals 0. Here they're the same. So y is going to be the lead coefficients, 5 over 7. Now this one, the degree is larger on top than on the bottom. So what I'm going to do is I'm going to actually break that up. This becomes y equals, and notice when I break that up, that becomes x minus 1. So this is the slant asymptote. And when we get to the graph, we'll have a better idea of what that means here in a second. All right, so let's do these 3 examples. So here we have the same degree. So the horizontal asymptote is at 4 over 7. They're both second degree. For part B, the degree in the bottom is larger than that at the top, so it's going to be y equals 0. And here, because the degree is larger on top than on the bottom, we have a slant asymptote. So let's divide that out using, in this case, long division. This one we could just break it up, but this one we're going to have to do long division. So we have x squared minus 3x plus 5. And we need an x here to get me the x squared plus 2x. Subtract, we get negative 5x plus 5. Looks like we have here. So here's technically what we're getting is y equals x minus 5 plus 15 over x plus 2. However, as x gets really, really big, that goes to 0. So basically our slant asymptote is at y equals x minus 5. So as x goes to either infinity, that goes to 0 quite quickly. All right, we are moving on. So here the the highlights of things that we're going to be looking for. First of all is the domain, meaning where am I potentially dividing by 0 when we're talking about rational functions. Those are usually relatively easy to find. The y-intercept is when x equals 0. So this is when x equals 0. Holes, you just need to factor and see if anything reduces out. X-intercepts, that's when y equals 0. Solve for x. Vertical asymptotes. Basically, if there's no hole, then whatever's in the denominator. So set denominator equal to 0. And those x values are going to be your vertical asymptotes. Again, unless they reduce out, you'll have a hole there instead of an asymptote. Horizontal asymptote, check the 3 cases. So 3 cases that we just talked about. It all depends on whether the degree of the numerator and denominator, how they compare to one another. The sign graph, I'm going to have to talk more about that in just a few minutes. That'll be whether the graph is positive or negative. We'll get to that, maybe not in this lesson, but in the lesson coming up. All right, so find the domain. So for A, let's go for A. The domain is x plus 2 equals 0. X cannot equal negative 2. So there's the domain in interval notation. Part B. X squared plus 1 equals 0, never. Now, if that was x squared minus 1, then we could factor it. But x squared plus 1 is always positive, because no matter what number we square, it's going to become positive. Then plus 1 is, again, going to be positive. So it's never going to be 0. Part C, we got x squared minus 4x minus 5 equals 0. X minus 5, x plus 1 equals 0. So x cannot equal negative 1 and 5. So interval notation is going to look like this. And I know that's kind of long, but that's what it is. And if you have even more factors in the denominator, you can see this could just go on and on and on. All right, part 2. So given the function, we're going to find the following. The domain in interval notation. Okay, so start part A here. The domain in this case is going to be x can't be negative 5. So it'll be negative infinity to negative 5, then negative 5 off to infinity. The y-intercept, that's when x equals 0. So f of 0 is 0 squared minus 5 times 0 plus 6 over 0 plus 5. So this gives me 5 over 6. So it's the point 0, 6 over 5, pardon me. Part C, the x-intercepts. Let's go up here for C. X-intercepts for y equals 0. This gives me x squared minus 5x plus 6 over x plus 5 equals 0. Multiply through by the LCD, it gives me x squared minus 5x plus 6 equals 0. And very nicely, that's factorable. X minus 2, x minus 3 equals 0. So this means that x equals 2 and 3 are my x-intercepts. So 2, 0, 3, 0. Part C. Part D, there are no holes. These do not reduce with the x plus 5. So D, no. E, vertical asymptotes, absolutely. That is when x plus 5 equals 0 or x equals negative 5. We have a vertical asymptote right there. Part F, there are no horizontal asymptotes. However, part G, or oblique, I'll notice that the numerator degree is larger than that in the denominator, so I'm going to divide it out. By the way, for the x-intercepts, had that not factored, you would have to use the quadratic formula. So x times x squared plus 5x, subtract negative 10x plus 6 minus 10, negative 10x minus 15 gives us 50, pardon me, 50. And that gives us a remainder of 56. So the oblique or slant asymptote is y equals x minus 10. We don't need to put the 56 over the x plus 5. That's, as I mentioned before, that goes to 0 as x gets particularly large to positive infinity or negative infinity. All right.